Alright, so let's say you're given this situation here, where a mass falls from a height of 5 meters to a height of 2 meters. And the question asks you, what is the work due to gravity between the initial height and the height of 2 meters? To start, we want to find the work done by weight when the object moves downward. So the object starts at a position of 5 meters and then ends at a position of 2 meters. This distance between the initial height and the final height is going to be this distance here, which we could denote as S, where S is the displacement and the direction is downward. And since work is equal to force times displacement, and the force is going to be equal to the weight force pointing in the same direction as S, they're both pointing downward. Work gravity can be defined as force times displacement, also equal to Fs cos theta, where theta is the angle between the force and the displacement. Since they're both pointing downward, theta is going to be equal to 0, and cos 0 is equal to 1, so we just get the work due to gravity equal to force times displacement. So we know that the force is equal to the weight force, which is equal to mass times gravity, so we can plug that in. And we know S is the displacement. If we look at our diagram, it's YO minus YF, so we can plug that in. And we can just rewrite it, denoting that Y1 is equal to the initial position and Y2 is equal to the later position. And then we can distribute the mg into each term. Now, important thing to note, if we remember U is equal to mgy, this is the gravitational potential energy. So we can replace mgy1 with U1, the potential energy at the first point, and then mgy2 by U2. We get this here. If we remember, the change in potential energy is going to be equal to U2 minus U1. So this expression here is the negative change in potential energy. So this is the final answer for the work in terms of the change in potential energy. And this shows that we can express the work due to gravity in terms of the change in potential energy of the object. When gravity does work on the system loses potential energy, hence why we see the negative sign in the equation. And this can be better shown by applying it to our example. So if we apply our equation and we write the change in gravitational potential energy is equal to mgy1 minus mgy2, we can plug in our known values where y1 is our initial height equal to 5 meters, and then y2 is our final height equal to 2 meters. To do that, we get this expression here, and then we can compute the amplitudes in the units. For the units, kilograms times meters per second squared, that's a Newton, so it's just Newton meters, which is equal to joules. If we compute the amplitudes in units for the other term, and we plug them both in, we do a simple subtraction, and we get this for the final answer. So this is the work due to gravity between the 2 points. So what is actually happening here? If we look at our diagram, at the initial position, our potential energy is 245 joules, and then at our final position here, our potential energy is 98 joules. We have our displacement here, and then we have our force due to gravity. Remember, work is equal to force times displacement. So the work that gravity does between these 2 points is positive 147 joules. So gravity does work on the system, which results in the system losing potential energy. It goes from the initial energy of 245 joules to the final energy of 98 joules as a result of the work of gravity doing 147 joules of work on the object.